Last episode, we learned the partial derivative, pick one axis, hold the other variable still, take an ordinary derivative. That gives us the rate of change in the x direction, the rate in the y direction, and so on. But from any point in the plane, there are infinitely many directions you can walk, not just along the axes. We need a way to compute the rate of change in any direction at all. The answer, beautifully, is a single vector. Stack the partials into a list, call that list the gradient, written del f, and the rate of change in any direction is just a dot product of the gradient with a unit vector pointing that way. Out of this one move tumbles a chain of consequences. The gradient points uphill, specifically in the direction of fastest possible ascent. The negative gradient points downhill. The length of the gradient tells you how steep the steepest direction is, and the gradient is perpendicular to the level curves of the function, which is the geometric heart of Lagrange multipliers, gradient descent, and most of vector calculus. Let's build it. Here is the definition. Given a function f of two variables, evaluated at a point a, b, the gradient of f at that point is the vector whose first entry is the partial of f with respect to x at a, b, and whose second entry is the partial of f with respect to y at a, b. That's it. We've taken the two scalar partials and bundled them up as the components of a single two-dimensional vector. In 3 variables, you stack 3 partials. In n variables, n partials. The symbol is the upside-down triangle, pronounced nabla or del, depending on which generation taught you. Both names refer to exactly the same operator. Note that the gradient is not a number, and it isn't a single vector. It's a vector at every point of the domain, varying with location. The mathematical name for that is a vector field. To every point in the plane, attach an arrow given by the gradient evaluated there. Brief history of the squiggle. The symbol itself goes back to William Rowan Hamilton, the same Hamilton who invented quaternions, who used the upside-down triangle as a generic differential operator in 1837. He never gave it a catchy name, he just called it the operator. The name nabla shows up later, around 1870, from James Clerk Maxwell. Yes, the Maxwell equations Maxwell and his friend Peter Guthrie Tait, both Scottish physicists working out vector calculus for electromagnetism. They needed a short word for the symbol and settled on nabla, from the Greek for a Hebrew harp shaped roughly like an upside-down triangle. Maxwell, in a letter to Tait, reportedly insisted on a name not previously appropriated, which is very on brand for Maxwell. The American name del, short for delta, came in through Josiah Willard Gibbs at Yale, who reshaped Hamilton's quaternion formalism into the modern vector calculus you learn today. So when you write del f, you are looking at a Scottish pun on a Phoenician musical instrument, drafted into 19th century physics and surviving to your textbook. Either pronunciation is fine, the operator is the same. Here is the question we want to answer. You're standing at a point, a, b, on the surface z equals f of x, y. Pick a direction in the plane encoded as a unit vector u with components u1 and u2. How fast is f changing as you step from a, b in the direction u? The formal definition is the same flavor of limit you've now seen many times. The directional derivative of f in the direction u, at the point a, b, is the limit as h goes to 0 of f at the perturbed point a plus hu1, b plus hu2, minus f at a, b all divided by h. The perturbation h times u is a step of length h along the direction u. One quick technical point. U has to be a unit vector for this definition to give the rate per unit distance. If you start with some arbitrary direction vector v that isn't of length 1, you normalize it first, divide by its magnitude, and use that. Otherwise, you'd be measuring the rate of change per magnitude of v steps, not per unit step, and the numbers won't match what people mean by directional derivative. Here's the punchline, the formula that makes the gradient earn its salary. If f is differentiable at ab, then the directional derivative in any unit direction u equals the dot product of the gradient del f with u. That is, the partial of f with respect to x times the first component of u plus the partial of f with respect to y times the second component of u. Why is this true? Differentiability of f means that near abf is well approximated by its linear part, the value at ab plus the partial of f with respect to x times the x displacement, plus the partial of f with respect to y times the y displacement. Plug in the displacement h times u. The x piece is hu1, the y piece is hu2. Subtract f of ab, divide by h, send h to 0. The leftover is exactly the partial of f with respect to x times u1, plus the partial of f with respect to y times u2, which is the dot product del f dot u. The partial derivatives in the axis directions e1, e2 are special cases. The directional derivative in the direction e1 is the partial of f with respect to x, and the directional derivative in the direction e2 is the partial of f with respect to y. So directional derivatives in arbitrary directions are linear combinations of the axis partials, weighted by the components of the direction. Now the headline theorem. Among all unit directions u, you can pick which one makes the directional derivative largest. In other words, which way is uphill the fastest. We just said the directional derivative is del f dot u. The dot product geometry from episode 2 tells us del f dot u equals the magnitude of del f times the magnitude of u times cosine theta, where theta is the angle between del f and u. Since u is a unit vector, the magnitude of u is 1, so the dot product simplifies to the magnitude of del f times cosine theta. The magnitude of del f is fixed. It depends only on the function and the point, not on u. So the only thing we can tune is cosine theta. It maxes out at 1 when theta is 0, that is, when u points in the same direction as del f. It bottoms out at -1 when theta is pi, that is, when u points opposite to del f. And it equals 0 when theta is pi over 2, that is, when u is perpendicular to del f. 4 facts all in one line of Cauchy-Schwarz. The gradient direction, u equals del f over the magnitude of del f, is the direction of steepest descent. Its opposite, negative del f over the magnitude of del f, is steepest descent. The maximum rate of ascent achieved in the gradient direction is exactly the magnitude of del f, and along any direction perpendicular to del f, the rate of change is 0. The function is, to first order, constant as you walk that way. That last fact is what makes the gradient perpendicular to level curves. Concrete example 1. Take the function f of x, y equals x squared plus y squared, which has graphed that familiar bowl-shaped paraboloid. Compute the partials. The partial of f with respect to x equals 2x, holding y as a constant. The partial of f with respect to y, holding x as a constant. So the gradient is del f equals the vector 2x, 2y. At a general point, the gradient points in the direction of the vector 2x, 2y, which is parallel to the position vector xy from the origin. It points radially outward, away from the bottom of the bowl. Now plug in the specific point 3, 4. The gradient is the vector 6, 8. The magnitude is the square root of 36 plus 64, which is the square root of 100, which is exactly 10. So the steepest rate of ascent at the point 3, 4 is 10. The unit vector in the steepest ascent direction is the vector 6, 8 divided by 10, which is the vector 3/5, 4/5. Notice that this matches the geometric intuition. On a circular bowl, the fastest way uphill from any point is to walk directly away from the center, straight outward along the radius. The gradient computes that for you automatically. Worked example 2. Find the directional derivative of f of xy equals xy at the point 2, 3 in the direction of the vector 1, 2. 3 steps. Step 1. Compute the gradient. The partial of xy with respect to x holding y constant is y, and the partial with respect to y is x, so del f equals the vector y, x. Evaluate at 2, 3 del f at 2, 3 equals the vector 3, 2. Step 2. The direction vector v equals the vector 1. 2 is not a unit vector, its magnitude is the square root of 1 plus 4, which is the square root of 5. Normalize, u equals the vector 1, 2 divided by the square root of 5. Step 3, dot product. Del f dot u equals the vector 3, 2 dotted with the vector 1, 2 over the square root of 5, which is 3 plus 4, over the square root of 5, which is 7 over the square root of 5. That's the rate of change of f equals xy at 2, 3 if you walk in the direction 1, 2. Sanity check. The magnitude of the gradient, del f at 2, 3, is the square root of 9 plus 4, which is the square root of 13, about 3.61. Our directional derivative is 7 over the square root of 5, about 3.13. The directional derivative is smaller than the magnitude of the gradient. It has to be. The magnitude of the gradient is the steepest rate, the maximum possible directional derivative. Walk in any other direction and you do worse. The numbers agree. Here is the picture. Blue circles are level curves of f of x, y equals x squared plus y squared, sets where f takes a constant value c. For this, f the level set f equals c is a circle of radius, the square root of c. So the family of level curves is a family of concentric circles. The red arrows are del f equals the vector 2x, 2y, drawn at 6 base points on the middle circle. Every red arrow points radially outward from the origin. And every red arrow is perpendicular to the circle it sits on, because the radius of a circle is perpendicular to the circle's tangent at that point. We've highlighted one tangent segment in teal dashed, with the little right angle square marking the 90-degree angle. Geometrically, this is what gradient perpendicular to level curves means. If you stand on a contour line and the gradient is pointing perpendicular to it, then walking along the contour keeps you at the same height. The directional derivative along the contour is 0, by the dot product formula. And walking perpendicular to the contour in the gradient direction gains height fastest. Why is the gradient perpendicular to level curves? 3 lines. Pick a point A, B on the level curve f of x, y equals f of AB. Let t be a unit tangent vector to that curve at that point. The function f is, by definition, constant along the level curve. So if you take a step in the tangent direction t, f doesn't change, to first order. That means the directional derivative of f in the direction t at a, b is 0, but the dot product formula says the directional derivative of f in the direction t at a, b equals del f at a, b dotted with t. Combine del f dot t equals 0. Two vectors with 0 dot product are perpendicular, so del f is perpendicular to the tangent, which is exactly the statement that the gradient is perpendicular to the level curve. In three variables, the exact same argument works for level surfaces. The gradient is perpendicular to the surface f of x, y, z equals c at every point, which is how we compute normal vectors to implicitly defined surfaces. That's a preview of Lagrange multipliers 2 episodes from now. Same idea in 3D. The blue mesh is the graph of z equals f of x, y, a smooth surface sitting above the xy plane. The red dot on the floor is our base point AB. Directly above it on the surface is the red dot at height f of AB. The red arrow in the floor, anchored at the base point, is the gradient del f at a, b, a vector in the plane, pointing in the direction of steepest ascent projected down to the floor. Lift that arrow up onto the surface and you get the orange arrow, the direction of steepest ascent on the surface itself. Geometrically, the gradient is a shadow on the floor arrow telling you which way to walk to climb fastest, and the magnitude of del f tells you how steep the climb is per unit horizontal distance. Where does the gradient actually show up? Everywhere. Machine learning first. The training algorithm for almost every modern neural network is gradient descent. You define a loss function, L, that measures how badly your model is doing, you compute the gradient, del L, with respect to the network's parameters, and you nudge the parameters a small step in the direction of negative del L, which is the direction of steepest descent. Repeat a few million times. That's the whole training loop. Essentially the same calculation we just did on x squared plus y squared, scaled up to a function on billions of variables. In optimization more generally, at any interior local maximum or minimum of f, the gradient must vanish, del f equals the 0 vector. If it didn't, you could improve f by walking in the gradient direction, which would mean you weren't really at a maximum. So the points where del f equals the 0 vector are the critical points where you have to look for extrema. In 2 episodes we'll meet Lagrange multipliers, which solve constrained optimization problems. The condition at a constrained extremum is that del f is parallel to del g, where g equals c is the constraint, a geometric statement about gradients perpendicular to level sets. In physics, the relationship that force, vector F, equals negative del U between a conservative force and its potential is one of the most useful equations in classical mechanics. Gravity, the electric force, springs, all derive from potentials by taking the negative gradient. And the geometric fact that del F is perpendicular to the level set F equals c gives you, for free, the normal vector to any implicitly defined surface, and therefore the tangent plane to it. Recap. The gradient del f is the vector whose components are the partial derivatives of f. In 2 variables, del f equals the vector whose entries are the partial of f with respect to x and the partial of f with respect to y. In 3 variables, 3 components. In n variables, n components. The directional derivative of f in any unit direction u is the dot product. The directional derivative in the direction u equals del f dot u. From the Cauchy-Schwarz dot product geometry, the gradient itself is the direction of steepest ascent. The negative gradient is the direction of steepest descent. The magnitude of del f is the steepest rate, and any direction perpendicular to del f gives a directional derivative of 0, which is why del f is perpendicular to the level curves of f. We did 2 computational examples. The gradient of x squared plus y squared is the vector 2x, 2y, which at 3, 4 has magnitude 10, and the directional derivative of xy at 2, 3 in the direction 1, 2 is 7 over the square root of 5. And the gradient powers gradient descent in machine learning, the critical point condition in optimization, Lagrange multipliers in constraint optimization, and the force from potential relationship in physics. Next episode, we generalize the chain rule to multivariable functions, with the gradient as the workhorse. That's the gradient and directional derivatives. One vector, del f, built out of the partial derivatives, controls the rate of change of f in every direction at once, via a single dot product. It points uphill the fastest, perpendicular to the level curves, and is the engine behind gradient descent, Lagrange multipliers, and the relationship between force and potential. If this helped, like, subscribe, drop a comment with the answer to today's challenge, for f of xy equals e to the x times sine y at the point 0, pi over 4, what is the direction of steepest descent and what is the steepest rate? The numbers come out clean. Next episode, we extend the chain rule to functions of several variables, with the gradient as the central object. Composition of multivariable functions is where partial derivatives stop being bookkeeping and start being genuine calculus. See you there. The gradient del f equals the vector partial f, partial x, partial f, partial y collects every partial derivative into a single vector. The directional derivative in direction u, a unit vector, is the dot product d us of a equals del f of a dot u. Cauchy-Schwarz pins down the extremes. The dot product is biggest when u aligns with del f, smallest when it anti-aligns, 0 when u perp del f. So del f points in the direction of steepest ascent, del f in the direction of steepest descent, and the magnitude del f is the steepest slope. Along a level curve f doesn't change, so the directional derivative there is 0, so del f is perpendicular to the tangent of the level curve. This perpendicularity is the starting point of Lagrange multipliers, and is the reason equigradient descent is the most famous optimization algorithm in machine learning. Next episode, the chain rule generalizes to multiple variables and the gradient is the workhorse. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.